I don't know.
I don't know if it's the changing.
All right, so here we are reviewing for the test on sections A and B. Would you like to talk to the camera? All right.
Hi, Corey.
You guys can say hi to Corey.
Hello.
Hello. Nice. Hey, Corey. Hello.
All right, so I suppose we can record this also for Steph. So Steph, we don't want to leave you out since you're not here. All right, so there's 3 smartboard files. There's the smartboard file for part A. There's a smartboard file for part B, and now we have the smartboard file that has the notes that everybody took on A and B. So these are all on the server. So here's 8.1, and so who did we have doing this one? Who was this?
That's the one with the fancy signature.
Who did 8.1?
Oh, that's Steph.
The part of Steph.
Oh, this is Steph? All right. All right, so we've got Steph's work here, and again, the first part is always that introduction to what is petroleum. So we've got crude oil is petroleum that is pumped from the ground. Refined petroleum is a mixture of hydrocarbons and is non-renewable. Petroleum can be used to provide heat for buildings, generate electricity, power, diesel engines, etc. Probably the main one that is left out of here is what? Gas. Oh yeah. For cars. It's probably a big one there. And the product part, I'm not sure if she gets to this in the next thing. But remember, I think I'd mentioned that this unit used to be called petroleum to build or to burn because it can be used both as a fuel source as well as to make materials or substances. Right. All right, and then so Steph seems to have focused on the reactions that produce energy here, and then I believe somebody else has that one picked up. I think that was Corey's actually, that we're looking at in more depth. Okay, and then we have 8.2, which goes along with the lab also in looking at how do we separate petroleum. So what was the process called when we separate petroleum? Huh? Distillation, we could even be more specific. What type of distillation? Fractional distillation. So fractional distillation is a little bit more than just distillation. Fractional distillation, you're going to have several different components that are going to be able to be separated out. Right? Whereas distillation, you normally think of as just like, for instance, separating salt and water. You would distill off the salt, or distill off the water and leave the salt behind. Distillation? Well, that's one thing it could do. Yeah, it definitely could do that. Right? And so we have our apparatus here that we had from our book. And the important thing here isn't that you can reproduce the picture exactly, but you understand what's happening. That you've got your mixture down here, and as you're heating that, what's the separation property? What property are we using to separate? Boiling point, yeah. Right? So the thing with the substance with the lowest boiling point is going to boil first and go here, and then it will condense back from that gas back to a liquid in the condenser coil, and then you end up with, there's a good word there, the distillate there. Oh, yeah, welcome. Yep, okay, so that's fine. Now this was an interesting thing. So it's good we got stuff here. So the density part. Where did you get the density part?
Well, it said in the book that like if you're trying to separate two mixture by density, that only works if they don't dissolve in each other. Like if they dissolve in each other, then you have to use distillation.
Good, yeah.
That's right. It's kind of an awkward sentence.
Right.
When I wrote it, that's what I was trying to say.
Yeah. So ordinarily, and this is Corey's not going to be able to see this, but remember we had did we look at this bottle before? Right. So when we look at the bottle with the blue and the white beads in it, if I shake this up, right, the white beads go to the top, and the reason is because that the liquids, there's two different things in there. There's alcohol and water and salt. And so the salt mixes with both the alcohol and the water when you shake it up, and it creates a density that's more dense than the white beads, but less dense than the blue beads. The blue falls to the bottom. As that salt then kind of migrates toward the water part, then that water part becomes more dense, the alcohol part becomes less dense, and then the white beads and the blue beads come back together again. So we could separate things based on density, but crude oil we can't do it because they're all mixed together. So we use the distillation. All right, good. All right, 8.3-8.4. So here we were lacking on, somebody didn't do their work here. Huh? Is that Allison?
I'm really sorry. I totally forgot. It's really
Allison. All right, so Corey, if you're gonna go egg somebody's house tonight, it's Allison. Don't apologize to me. Apologize to Corey and the rest of the class.
Sorry, Corey. I'm sorry, class.
Who has A5?
So let's take a look at A, 3, and 4. Fortunately, we have Mr. Horsley's awesome notes here, right? So 4 and 5. So in this part, we left off stuff, right? I'm not sure why we left off all of this stuff. Right. So and this was on the quiz, before we looked at, where is the world's petroleum? Because it's, the bottom line is that, there's a lot of political and, foreign policies that are affected because of petroleum and how important it is as a resource to us. So that's a really important part of, this unit. So we don't want to lose sight of that. The research project, there. Right, there's our picture that they drew. The different fractions, and again, knowing where things fall into the different fractions. You should know the general area where things would be found, right? Plastics aren't necessarily at the top. Plastics aren't up there. There's no plastics in crude oil. But some fractions of them are used to make plastics. Okay. Okay. So then we had, where does a barrel of oil go to? And this was in 2009. So we can see that most of it goes into gasoline for our cars, and then we've got the other products, the liquefied gases. So, to have kind of a general idea of, where that fuel goes. Is important. Not specific numbers, but the size of the molecules. Right. So if we go back to here, diesel fuels. All right, here are diesel oils. Right, and here's gasoline. So I believe that the diesel fuel is somewhere down in here. In the C, this range here. Okay, whereas gasoline is up here. So the larger molecules. Makes it difficult for diesel cars in the wintertime, right? Because what else is true? If the molecule's bigger, it's harder to separate the molecules, right? Because the attractive forces are stronger. So they end up freezing. The liquid becomes very, very viscous in the wintertime. So if you have a diesel car where in a really cold climate, oftentimes what you have to do is plug it in before you leave, or before you're going to start it up. And there's a heater in there that heats up the fuel so that it'll actually run.
It's really a long time for my truck to go.
You have a diesel truck? Yeah.
Two questions about diesel cars. Why is it that diesel you get more gas mileage with it than gasoline? And why is it that diesel cars tend to have less horsepower, but they'll have more torque? They'll they'll have a higher rating for torque and less for horsepower, but gasoline is kind of the same.
Right. Well, maybe Dan can answer that part.
Why is it that diesel cars have more? They generally have higher gas mileage, and then for some reason you you get more torque out of a diesel car, like than like you would necessarily with such.
Well, the torque is a transmission issue. It's not necessarily the power of the car, but it's how you set up the transmission for it. So obviously trucks need a lot more torque. So, and the efficiency of the fuel, the mileage has to do with the bigger molecules and how they burn in the engine.
Oh yeah, the idea of like you get as much more energy you put in necessarily, you might get more energy.
Right, per gallon, yeah. So, okay. Okay. All right, so we got all that stuff there. All right, so the molecules in petroleum. So this is the next section. We wanted to find out what it is about the molecules. And I think, again, if I go back to our summary here, we had the part that Allison kind of skipped off on there. Was it we were just going to keep bringing that up. Now, it had to do with actually it had to do more with the fractional distillation and the hydrocarbon boiling points. And then nobody do the chemical bonding? I don't know. All right, so that was, the chemical bonding was Jack, right? So Jack's looking at chemical bonding for us in 6-7. Okay. Now, here's a problem, though, in that there's not a whole lot there about chemical bonding, right? And you did, what's this? Maybe it's more of it's here. Okay, here we go. So here's a little bit. So organic chemistry is a branch of chemistry that's focused on hydrocarbons. So hydrocarbons are what? Yeah, we need probably a pretty more serious attitude right now, right? Okay. So hydrocarbons are compounds with what? Carbon atoms and hydrogen, yeah. So and the carbon forms the backbone. So the carbon chains are the ones that are going to primarily determine the shape of it. So it's when we draw these things, we usually draw the carbon chains first, and then we add the hydrogens in after. Right? So remember drawing the different isomers that we did? Okay. They involve covalent bonds. So in terms of our bonding that we talked about, the covalent one is going to be the most important. And again, that's where we're, Jack did a pretty decent job here, but not nearly enough about bonding that we need. So let's go back over to the other bonding one real quick and make sure that we've got that stuff here. So our general ideas, we have covalent, ionic, metallic. And then, remember, we have this slide here. So, ideally we understand this slide, right? The different types of bondings, the ionic up at the top, and then covalent, and the metallic down at the bottom. Some of the keys are why these things hold together. So the ionic, we've got the positive ion and the negative ion attracting because they're oppositely charged. Covalent, we have that sea of, or not the sea of electron, but we've got all this electron density between the two nuclei that are attracted, pulling both nuclei towards it. Right? And then the metallic. And Jack did get into that the important part here were the valence electrons. So that idea right there is critical too. It's the valence electrons that are going to be involved in the bonding. Here. Right, those outermost electrons. Right, when we think about metals as having only a couple of valence electrons usually. Non-metals tend to have a lot of valence electrons. So the metals tend to lose electrons so that they kind of shave down to a full shell, right? Because what's underneath the outer shell, the valence shell, is a full shell. And non-metals will tend to gain electrons to put a couple in to fill up their shell. Right? Make sense? And that full shell is the stable octet. Right, so when we look at the dot structures, where's Jack's dot structure? Yeah, here. We can look at carbon, and the carbon has 8 electrons around it. Hydrogen only has 2. Remember, hydrogen's a little special. It only needs 2 electrons to be happy, right, to be stable. Okay, and then going down to more of his, the tetrahedral shape, very important term there. Okay. Yeah, a lot of it's biological in nature too. I mean, we talk about petroleum, but that organic or that tetrahedral shape of the carbon is also what's involved in all of our, all the proteins that make up our bodies. Most of the, the DNA and RNA and all the other stuff that's in our bodies. Okay, and then we had different types of formulas. We had the molecular formula, condensed formula, and did you get into the isomers? Was that part of yours, Jack? I don't know if that was part of yours or you did 6 and 7?
Yeah, that was the isomers were mine on 8.8.
Okay, right. Okay. So here, I'm not sure how well you guys can see back there, but we've got the straight chain alkanes. And, if we're going to draw pictures of these things, straight chain, we can do something like that. If we're going to make an isomer of that, we have to make sure that we don't just turn it, right? We have to make sure that we actually take a carbon off and put it someplace different. And then what we would do to make a complete dash structure here is we'd add in the hydrogens. Right? And around each carbon, there has to be how many bonds?
Well, depending.
Now, around each carbon, how many bonds does it have to have? 4, right? So anywhere where there's less than 4 bonds, you would then put in enough hydrogens to give yourself 4 bonds. Okay. Boiling points. This is a really critical thing here. The relationship between boiling point and the chemical structure. Right? And so it looks like Felix took care of this for us. So more atoms yields a higher boiling point, so the larger the molecule. Right? And the fewer branches on the molecule give you a higher boiling point also. So the straighter the molecule is, the higher the boiling point would be also. Right?
I remember whenever this, I said something on it again. My explanation is a result of the surface area for the
Sure, yeah, the contact that they can have. Right? So the idea is that if you have a straight hydrocarbon chain, there's a much greater area of contact. It's like taking a spaghetti, 2 strands of spaghetti and putting them next to each other. There's a lot of area where they can contact versus a ping pong ball. Right? Take 2 ping pong balls. There's only a small point where they can touch and make contact. Right? See the difference there? Yeah. So the longer chain you have, or the straighter the chain, the better. B.1. All right. So that was the ending of section A. And there is the question there about fuels and climate, the section 8.11. It's kind of that idea I was talking about. That, I mean, if you had a fuel that was that had larger molecules in it in a really cold environment, it's likely that it's going to become really viscous and not work well in the wintertime when it's cold. So. All right, and then section B. So B.1 was Corey. So Corey, sorry you couldn't make it. All right. We'll go over to this section here. And B.1, right, our buried sunshine idea. Right, where all the energy from petroleum originally came from organisms that had died a long time ago, and they got their energy from sun through what process? Photosynthesis. Good. Right. And then this got us into all the different types of potential and kinetic energy, which I think Dan covered a little bit, so we'll come back to some of these, right? You did that? Yeah. And then we had our different forms of kinetic potential energy, right? Which we should be, I mean, obviously mostly familiar with the chemistry ones, right? Which are stored chemical energy because of the way atoms are arranged. And then the kinetic part of that is the motion of the molecules. Right? So if something releases energy, a lot of times the kinetic energy that comes out of that is making the particles move faster, which we think of as heat. Right? Light is another one. Right? Light is another form of kinetic energy. right? Light travels. Sound, that kind of thing. Electricity in batteries, right? When stored chemical energy in a battery is used up, it produces electricity, flowing electrons. All right. And then we had our pictures here. And remember what we tried to do? We spent a lot of time working on this, a lot of time working on this, a lot of time working on this, right? Which is what? Who? A lot. When you look at the reaction, when you look at a reaction like this, you want to think of it in two parts. Now, from the energy standpoint, you want to think of two things that are happening, right? You got to put energy into break bonds, and what? And how much? And you get energy back out when you form the bonds. So, how much energy did we have to put in? Right here. How much energy do we have to put in to break the bonds to form all those single atoms there? And then how much energy do we get out when we form new bonds? Okay, and the difference between those two tells us whether it's exothermic or endothermic, the overall process. The breaking is always endothermic. The forming is always exothermic. And then overall, we would look at it and say, well, there's this much we had to put in, right? That much energy we had to put in, this much energy we got out. So the net result is that we gave energy off. All right, so I think that was all of Corey's stuff. So B.1. All right, and the B.2 and B.3, so this is Dan's. And so we got law of conservation of energy, all right, saying that whatever energy is transferred, we have to account for it somewhere, right? What's the big issue with this in cars? Yeah, not 100% efficient, but not even close. It's like, yeah, it's really, really inefficient. So a lot of the fuel that we're using is used inefficiently. So, so we did some calculations with, well, how much gasoline do we use efficiently? How much gasoline could we save if we were more efficient, right? So those are some kind of big questions for us. But at this point, we don't really have a choice, right? In terms of
involved with conversion factors.
Yeah, this is part of it, right? I mean, we went through, I think it was Jack and Allison and Corey and I went through and just did a bunch of, Rachel, sorry. Went through and just listed all the different conversion factors that we did, in these sections. So one was, how many miles does your car go per gallon? How many dollars do you spend per gallon? How many miles do you drive per year? And so there's that list of conversion factors that we would use if we're faced with this problem, right? And one of them that was the efficiency, like a conversion factor for efficiency. So we said that if a car was 25% efficient, that means that for every 100 let's say kilojoules of energy, only 25 kilojoules was used efficiently. Right, so you could set up a kind of a conversion factor that way, or even if it were gasoline, for every 100 gallons of gasoline, only 25 gallons was used efficiently, that kind of thing. Right? How much money would you save if it was 100% efficient? Right. Well, a similar thing. So energy is the energy used.
That was.
Yeah. What's that there?
That was the next. That was
B.3?
Yeah. That was the question.
Oh, okay. I see. So, yeah. So the picture we're missing there. Let me see if I have that in my thing here. Can I put that in here? Yeah. All right. So looking at energy conversions was another thing. So I'll probably ask you to do this. I probably wouldn't do a car. I'll do something different, right? But I'll ask you to explain the flow of energy. What form is it in? Is it kinetic or potential? And kind of describe how energy goes from one form to another. Well, you can do both, right? Like if I said, for instance, if I were using like a flashlight, yeah, you'd say, oh, well, I've stored chemical energy in my battery. That stored chemical energy, the chemical potential energy, is then converted to electrical energy, right, which is kinetic, and then that's converted to light, which is also kinetic. Right, so you see how you can flow. You can describe it both as potential or kinetic and what form it is. Okay, and back to our review. Oops. So 4-5. So I think that was the same thing, like the car. Oh no, 4-5 was, who had 4-5? Was that you? All right, so again, Corey, you can go at Dan's house for not doing his work here. So let's go over to there. Energy efficiency, and so this is what we did. We started doing some more of our dimensional analysis things, and yeah, looked at different conversion factors there. Okay, and again, we spent time doing these things. We don't have time to go through all of it all over again, but again, what's going to be useful is that you kind of have a handle on what conversion factors you would use, right? Or that would be available to you. And then we had all those efficiency questions. The combustion lab, which we're skipping. And then we did some conversion factors with this stuff, and this was, who is this? This is Rachel, right? So Rachel went over and did B.7 using heats of combustion. So this is where the conversions where we said, oh, well, if this many moles of hexane burn, how much energy would be given off? Yeah, that kind of thing. Heats of combustion questions. All right, so so Rachel actually did a couple of good questions for us here, which we could try and go over and answer if we have a few minutes. And then altering fuels. This was a section we didn't cover in class, but I did ask Rachel to jot down some notes for this. So we'll include her notes as legitimate stuff for the test. So cracking. Cracking is applying thermal energy or catalyst to large hydrocarbon molecules to crack them or break them into smaller molecules. So why would we want to break them into smaller molecules? Well, just so we could use them for a different purpose, right? I mean, when we look at the fractionating tower, remember there's some of the fractions are going to have hydrocarbons that have large numbers of atoms in them, and so we might not need that many of those. So we break them apart into smaller ones that we could use. Catalysts, good word there, used to increase the speed of a reaction. And that's an interesting point, is that you can, if you use a catalyst, you can be at a lower temperature. Right? So you don't have to heat up the hydrocarbon to break it apart as much if you use a catalyst. That was a good thing. Octane rating just talks about the types of molecules that are in the gasoline. And again, the octane rating influences how quickly the engine burns the gasoline. Right? I mean, and, you guys probably have to pay attention to this pretty carefully in your cars, right? I mean, is it I mean, what kind of fuel? I mean, do you guys use a particular octane of fuel in your cars, or?
I think I'm not sure. I forget. I used to know what it was.
Okay. Well, you've probably checked into that, and then you can come back and let us know. Let's make sure we're okay time-wise. Good.
It might be around 12.
Around 12?
Yeah.
Okay. All right. Oxygenated fuels. So oxygenated fuels are blended with gasoline to enhance the octane rating. Okay, what is an oxygenated fuel? Well, it really means just taking that molecule that before had just carbon and hydrogen and adding oxygen to it. Right? Now, the simplest thing that we can create that has oxygen with it, in addition to this, are alcohols. So you get gasohol. Right? And the neat thing is that we can make this from corn. Right? You see ethanol? Yeah. And why is that an advantage over using petroleum? Making it what? A renewable resource. Excellent. Good. Yeah. So all of a sudden now, and most gasolines are 10% ethanol. You have to be really careful, because like water sport stuff, Sea-Doos and all that kind of stuff, you really shouldn't use ethanol gasoline in those. So you have to be careful where you buy your gasoline. But almost everywhere, your gasoline is 10% ethanol.
Like that vegetable oil gas that use?
No, that's another one. That's biodiesel.
Biodiesel.
Yeah, so biodiesel has to go in a particular kind of car, or the engine has to be designed for it. The ethanol, they can put in 10% ethanol, and it won't affect how the car runs. But some of the smaller engines, like the ones in jet skis and things like that, don't operate well with that.
I heard an argument against ethanol because I think the rationale was that would increase the farming of corn and therefore destroy actual land that is farming nutrients.
Yeah, excellent point. Don't get the impression that that any one method of energy is going to solve all of our problems. Everything is going to have a negative side to it. Right? There's always a cost, or there's something that's going to, 'cause otherwise we would have switched.
Yeah.
Right? If it were a simple no-brainer, well, this is the best energy source, let's just do that, we would have already done that. Although, who tries to prevent those kind of things? Yeah, lobbyists. Right? I mean, you guys talk about lobbyists in government? Do you guys say government yet? Yeah.
Yeah.
All right, lobbyists, I mean, like the whole gun debate. I mean, do you really think that most of America wants us to have assault rifles out there in the general public? No, that's insane. So why won't government actually pass laws that prevent that? Because of the NRA. The NRA has one of the most powerful lobbyist groups in the country. I mean, the politicians, basically get a lot of their contributions from those people. So. They're very big, yeah.
And it's all of these giant groups, like the sisterhood of like Charity and Mary, and the Virgin Mary is like the most despicable group on earth.
Right.
Like they make it so that they can charge you $3 for something that costs like 5 cents to produce.
Right.
They have like this weird.
Yeah, I mean, government is such a frustrating place, because you can take something like gun control, and where you know that, all right, this is wrong. We should be able to come up with bills for this, right? But the thing is that in order to get people to vote for it, then you've got to kind of agree to vote for something else that you might not believe in wholeheartedly, right? Or the bill might include something else that isn't something you believe in. So politics it's a really, really complicated process.
The other thing is that since everybody need money to run a re-election campaign, therefore the people who
Right.
are most influenced on these people is going to give you the most money, and unfortunately people are making a buck out of all of these industries.
Sure. Yep. Okay. And then the last one up here was the isomerization, and yeah, not horribly significant. You can probably forget that one in terms of field, but it's just coming up with alternate ways to to generate a fuel that can burn in the car by changing the structure of the molecule rather than adding oxygen. Right, so they're just some different methods there. Okay, so we can go back. We want to go back to Rachel's examples here. She has some problems that we can try. Where did Rachel's problems go? Rachel, what problems do you have? Where did they go? Oh, it was the last one. We were right there. Oh, yeah. Sorry. All right. So what have we got? So how much thermal energy does burning 2 moles of pentane produce? Right. And maybe this isn't horribly difficult. So 2 moles of pentane, which would be C5H. C5H what?
C5H 12.
12, good. Over 1. And so we would say, well, 1 mole of C5H12. And let's go over to here. Oh, yeah, it's in the right place. C5H12 here. And which number am I using? The 48.8 or the... Yeah, you want to use the one that's moles, right? So we'd use that one. Okay. All right. So I'll be around for a little bit after school today, but not too long.
What time will you be here until?
Probably until about 3:15.